Hello, so today we will be discussing about the vertical motion in a resisting medium. If you are considering the vertical motion, just remember that either a particle it can go upwards, or we are discussing when the motion of a particle is downwards. So always remember that if a particle has to go upwards, you have to supply some initial velocity. Whereas if it is falling downwards, an initial velocity may not be required. Okay, and also what do you need to know here? Over here, just remember that the velocity at the highest point is zero. Okay, so if a particle or if a body is traveling upwards, surely it has to come back down. So the particle at the velocity at the highest point is zero. That is very important information. So what are the type of problems that we will encounter here? Naturally, we will have to do the same things that else. We will have to find a relationship between S and T, sometimes between V and T, and sometimes between V and S. Okay, S, you can even use X, it doesn't matter, all right, but you just have to be very careful that it should denote the displacement. So you can either use S or X, depends. Okay, but according to the books that I am using, this is what they usually do when they are studying vertical motion. Instead of S, they are using it with X. For horizontal motion, they are using S. Again, it is just a matter of notation. You can use any symbol that you like, either S or X. So besides this, you will also be required to know something more. Okay, we have discussed something about the terminal velocity. So what is the terminal velocity? So experiments have proven that if you are dropping a body from a very huge height, there comes a point. Okay, so if you are just dropping it, so the velocity of particle at that point will be zero. So the velocity keeps on increasing. It keeps on increasing. There will come a time when the velocity becomes constant. That is, this is the highest maximum velocity that the particle can reach. After this point, even if it travels downwards, the velocity will remain constant. So the velocity over here in this case, that is the terminal velocity. Okay, so because the velocity is constant in that case, so the acceleration, it will be zero. So you can define terminal velocity as the velocity when the acceleration is zero. So that is why over here in vertical motion in a resisting medium, we also have to see these two types of questions. Sometimes, can the terminal velocity be reached? Is it possible to reach terminal velocity? Because as I have said before, if you are dropping it from great height, terminal velocity may be reached. Okay, but if you are dropping it from a very short height, maybe depending on some conditions, terminal velocity may not be reached. So one of the questions attached is, can the terminal velocity be reached? That is what we will investigate in this motion. Also, what do we have to find? If a particle is projected from below, if it is traveling upwards, we also have to find the greatest height that the body can reach, and also what is the time taken to reach this greatest height. This is what we will do when we are investigating the vertical motion in a resisting medium. So this is enough. So now let us just go ahead with some examples. Again, the usual method that we will be doing, we first have to form the equation of motion. Afterwards, we either have to see whether we will use dv dt or ds dt, okay, depending on what we want to find. Okay, so now let us try this example. Let a particle fall in a medium whose resistance per unit mass is k times the velocity. If capital V is the terminal velocity, show that all these things. Okay, so over here what we will be having is this kind of a picture. Okay, so the particle, it starts from O, okay, where the velocity is 0. Okay, velocity is 0. Then after some time it will reach a point P where x is the distance from O, v is the velocity, small v, and small t is the time taken from O to P. Okay, we have to show all this, and capital V is the terminal velocity. If you take a look at this relation 1, okay, capital V, because it is terminal velocity, so it is a constant. 1, it is a constant, E, it is a constant. Similarly, the acceleration due to gravity is a constant. So this one is a relationship between small v and small t. This one is a relationship between x and t. And this one is a relation between x and small v. This one is capital V. Okay, so now, okay, we will just proceed as usual. Okay, first we will form the equation of motion. So the equation of motion is, okay, so what are the forces that this particle is experiencing, or this body is experiencing? Okay, let me just write it down. mg minus mkv. How did I get this one? Okay, because the way it is mg, it is always acting downwards, and because it is falling down, so the resistance will be upwards, so it will be mkv. The resistance is mkv. If you have to say what is this equation, how this one is actually, this is the force experienced by the particle is equal to its weight minus the resistive force. Alright, the force experienced by the particle is equal to its weight minus the resistive force. Okay, so I hope that is clear. Okay, if you take a look again at relation 1, it is a relationship between velocity and time. Okay, so it gives us an idea that we will have to express this one. It is the acceleration. We can write it as dv dt. Okay, g minus kv. In this point, okay, so I don't need that one anymore. Once you have this equation, okay, for the downward motion, okay, this one is downward motion because it is falling down. Okay, so once you reach this point, just remember that you will have to also obtain an expression for the terminal velocity. Okay, so when I will write it to the side, when capital V is the terminal velocity, we can have that the acceleration is 0, but this one is the acceleration. Okay, so 0 will be equal to g minus k capital V. Okay, or in other words, g equal k capital V. So this one, just name it as equation A. Okay, so what we will do is now we will substitute g equal kv over here. So we will be having dv dt g. Okay, we will be having this k small v capital V small v. So we can take common k and then separate the variables. We will be having something like this, k dt. Okay, and then we integrate. We are integrating from the point O to the point P, so that's why the velocity at the point O is 0. The time at that point is again 0, and over here it's V, over here it's t. Okay, from the point O to the point P. Alright, So now we just have to know this integration. If you take a look, this integration is very similar to integration dv upon v. Integration of this one, it is log v. So we will do this integration directly without any substitution. Okay, it helps a lot. So always remember, because we are having only one variable v, so what can we do? This integration, if you replace it with a linear polynomial a plus bv, again will be the same thing. The coefficient of v, it is b, so the result will be similar, but we just have to divide it by b. Okay, so this is what we will be having. Similarly, if we use that over here, we will be having minus log capital V minus V equal kt. Okay, and over here we will be having the limits from 0 up to V. Okay, so minus kt, actually you can write it here, minus kt. So now we can just substitute the limits in this left hand side. The limits will be something like this. Okay, substitute the limits in place of v. We will be having this. So now then we will have this, or minus kt. Okay, we are almost done with the first part. Okay, I will just write it down. Then we will be having this v minus v e minus kt. Okay, so this is the required expression, but if you take a look at that expression 1, in place of k, they have used g upon v that we got from a. Okay, so we will be having this. Okay, 1 minus e, instead of k, we will be writing g upon v, capital V. Okay, so this is the required expression 1. Okay, now if you take a look at relation 2, it is a relation between distance and time. So if it is a relation between distance and time, okay, instead of v, we will replace it with x, dx dt, sorry. So we will be having something like this. Again, now we just have to separate the variables. dx 1 minus e minus gt upon v dt, integrate. Now we are integrating again from the point O to the point P. At the point O, the distance is 0 because it is starting from that point. At the point P, the distance is x. At the point O, the time is 0 and it takes time t to reach the point P. So we will be having this. Substitute the limits. Capital V, it is a constant because it is a terminal velocity. Right, so we'll be having this. Okay, integration of 1, it will give you t minus integration of this one. Okay, it's similar to integration of e power minus x. Okay, we'll be having something like this, minus v upon g e power minus gt capital V. Okay, the time is from 0 to t. So just try to simplify it. Okay, substitute the limits now. T plus v upon g e power minus gt upon capital V. Time is 0, so minus 0 minus when the time is 0, so e power 0 is 1 minus v upon g. So this is what we will be having. So now we just have to simplify it. Okay, let's see. Okay, let us try to simplify this expression. X, okay, x will be equal to vt, v square upon g, e power minus gt upon v minus v square upon g. Okay, so this is the required expression if you see. Okay, actually they have taken to common v square upon g, e power minus gt upon capital V minus 1. Okay, so this is the required expression between x and t. Okay, so this one is number 2. Now we have to find a relation between v and x. Okay, now we have to find the relation between v and x. We cannot proceed from over here. Okay, but what we will do, again, we will go back to the original equation of motion, which is again, okay, the equation of motion, if you remember, after simplifying, we are having something like this: dv dt equal k v minus v. If you remember that we have got something like this. Okay, since we want a relation between v and x, okay, we want this relation between v and x. What we will do is, instead of this acceleration written this way, we can write it another way, which is v dv dx. Okay, capital V minus v. Okay, again I repeat, how did I get this one? It is from the first few lines at the start of the problem, and then we have replaced dv dt with v dv dx, small v over here. This is small v. I am using this expression for the acceleration because I want a relationship between v and x. This is capital V minus small v. Okay, so now we will separate variables. K dx. Integrate in. The limits will be from 0 to x. Limits will be from 0 to v. Next, okay, how will we integrate this? Okay, if you see this one, it is linear, and over here on top also it is linear. So again, okay, I don't want to use any substitution. Of course you can do substitution, but that will just create more confusion in the board. Okay, it will actually increase the number of steps. So I would like to do this integration directly. So how would I do it? Just see over here in the denominator we are having minus v. Okay, so I will try to get minus v in the numerator as well. So I can write it like this: multiply both sides by minus. Okay, if you multiply both sides by minus, so you'll be having something like this. Okay, multiply by minus. Okay, actually so you'll be having something like this. Okay, next, what do I need? I need v, capital V minus v. So now what I will do here is, because since I need capital V minus v, I will add. So I'm adding v. Next, what will I do? I will subtract v. So this is what I will have. Now what do I do once I reach this stage is I will split the integral. V minus v, take it as 1, okay, divided by v minus v, you will get 1, capital V, v minus v dv. So you'll be having something like this. Next we integrate, you will be having v, capital V, it is a constant. Again, the integration of this one will be minus log v minus v. Okay, something similar that we had done. Okay, so something like this you will have. After this, what I will do is I will substitute the limits. Okay, the rest of the steps, they are similar. So I keep on repeating this statement. Over here, you won't find any problem. The only problem is in finding the equation of motion and in integration. If you are comfortable with finding the equation of motion and if you are comfortable in integration, you won't find any problem in this chapter. So okay, substitute the limits. Okay, maybe I'll just write it first. Substitute the limits. We will be having something like this. Okay, minus 0 minus log v. Okay, equal minus kx. So v plus log minus kx. Okay, if you remember, k, it is gx upon v. Okay, because if you remember, the expression was g equal kv. So k will be g upon capital V. K will be, okay, so this is the required expression number 3. Okay, expression number 3, it is this. Okay, I hope I did not make any mistake anywhere. Okay, it seems fine. Okay, so this is the required expression, that is expression number 3. Okay, just multiply both sides by minus. Okay, and then you will be having it. Sorry. Okay, I think I forgot capital V. Okay. I forgot capital V here. Okay, I forgot this capital V. So everywhere just put in capital V. Okay, which is the required expression. Okay, so this is the required expression. Multiply both sides by minus. Okay, so we'll be having minus v log v minus v upon capital V equal gx upon capital V. So this minus, okay, just interchange the log. So we will be having something like this. Okay, this minus sign. Okay, interchange, reciprocate the log. Okay, and then remove this minus sign, you will be having plus, but you will have to reciprocate the logarithm, the terms inside the logarithm. Okay, so this is required expression number 3. So it looks like we are done. Okay, but we are left with one more thing, that is, can the terminal velocity be reached? Okay, now the only thing that we have to solve is this. Can the terminal velocity be reached? Okay, for this, always remember, if you are seeing this question, first what do you have to do? You have to find a relationship between v and x. Next, which is this number 3. Okay, this is a relation between v and x. Okay, so let me just write it down now. Gx on capital V. Okay, which is this expression over here. This is a relationship between x and v. As v approaches, so sorry, I made a mistake. As v approaches the terminal velocity, what will this expression give? Gx upon v. V approaches terminal velocity. Okay, so if you are substituting it, okay, you will be having something that looks like this. V minus V. Okay, approximately, okay. The limit of this one, it looks like it is going to be infinity. Okay, because log over here will be undefined, right? It is undefined because we have say that the velocity approaches the terminal velocity. Okay, so what we will be having is gx by v, it will be undefined. Okay, undefined, or will approach infinity. It will approach infinity. So that's why we can say that x from this step, okay, because v and g, they are constant, we can say that x approaches infinity. So the terminal velocity, it will be reached when x approaches infinity. In the real case, okay, in reality, this cannot happen, okay, because the distance is at an infinite distance, okay, which is impossible, okay, because we are studying that the particle is falling down, okay, so we'll have a fixed distance, okay, the distance can never be infinity, so impossible. So that is why from these we can conclude that the terminal velocity, it cannot be reached. That is enough for today. Okay, next time we will discuss the vertical motion in resisting medium again, but when the body is moving upwards.